Hello everyone, this is Xing from Ohio State University. My project topic is demonstration of 3.3 kV silicon carbide MOSFET Schottky diodes in next-generation fast charger circuits. Professor Jing Wang is a supervisor from Ohio State University, and we have Dr. Ranbir Singh from the GENESIC as a project collaborator. Students who are working on this project include me, Xiaoli, Zhining Zhang, and Harsh Banisha. There are three milestones for this project. The milestone 1 includes the device dynamic evaluation through the double hose test and the device overcurrent protection. And in the milestone 2, we will use the device we evaluated in the milestone 1 to build a half-bridge structure. And this half-bridge structure, some module will be used for the single-phase MMC, and it will be tested at 7 kV DC voltage. Benefited from the high voltage rating. For each arm, we will only need 3 sub-modules, while each sub-module will have about 2.3 kV voltage applied on it. And then for the milestone 3, we will use the same sub-module we built in the milestone 2 to build a 3-phase inverter and test it at 2.5 kV. And according to the DC voltage rating, there will be 1 sub-module each arm. The single-phase MMC test configuration is shown in this page. The total apparent power is 13.4 kVA. The output frequency is 1 kHz, and the sub-module switching frequency is 10 kHz. That switching frequency is related to the gate driver part. The input voltage is 7 kV, and the sub-module voltage is 1/3 of the input voltage, which is around 2.3 kV. The RMS load current, according to the SOPO, is 20 amp, and then in the simulation, the arm current in RMS is around 11.3 amp. The modulation index is 0.27, and the power factor is 0.01, which means the load is almost a pure inductor. Control system block diagram is shown in this page. In the power side, we have the current sensor and some module including the gate driver and voltage sensor. The current sensor will send out the arm current to the DSP, and the gate driver will receive the gate switching signal from the FPGA and send out the full signal to the FPGA. And the voltage sensor will send out the capacitor voltage of each sub-module to the FPGA. The FPGA will communicate with DSP regarding the feedback from the circuit and try to give the correct signal to the gate drive. Then the DSP will also work with the human-machine interface. This page shows the sub-module thermal calculation. And based on the device evaluation and circuit simulation, we can know the information of the conduction loss and switching loss. And for the thermal resistance part, the junction to case temperature resistance, the thermal paste resistance, and the heatsink resistance is shown in this page. While the heatsink is one heatsink, and we have wind cooling for that. The total resistance is close to 1 degree Celsius per watt, and the junction temperature will be around 102 degrees C if we have 40 degrees C in the air. That is within the device operation temperature. The 3D drawing of MMC sub-module is shown in this page, and from the top view, you can see we have a 4 sub-module capacitor here. And for the upper PCB, it is a voltage sensor, and the lower PCB, which is the gate driver. We use the fiber optics to receive the gate signal and send out the fault signal. And for the thermal design, you can see we have 2 fans and 1 heatsink for each sub-module. That's the end of my presentation. If you have more questions, you can contact me through the email or Professor Jing Wang. Thank you very much for listening.